SwayamPrabha. Digital India. Educated India.
Okay. So, there are by now several fully homomorphic encryption schemes. The one that I will show you is the cleanest one of them all, not necessarily the most efficient one, but very easy to understand. So, this is by Gentry, Sahai, Waters. Okay. It is called the GSW FHE. So, there is a setup step. So, we will before doing key gen, we will just break up key generation into two steps. So, one is a setup step where we choose a random matrix, we make it available to everyone, and then we will do key generation using that. This is useful later just to divide the key generation into these two steps. So, anyway, let me tell you the scheme. So, if so my setup here, it takes my security parameter. It also takes the depth of the circuit that this scheme is going to support. So, remember we defined homomorphism with respect to a circuit depth. It will become clear to you why we need to worry about the depth. Okay. So, what this will do is it will choose the basic public parameter. So, it will choose a modulus Q, it will choose matrix dimensions n and m, right. It will choose the noise distribution chi that we are familiar with from LWE. Okay, and some some noise bound, actually okay, we can call it noise bound. So, some noise bound B chi. So, B chi is the the bound of a sample of chi. We have seen this before, right. So, when we looked at public key encryption from LWE, we said that the error will come from some distribution, we will bound the size of the error. So, we are just giving the bound a name. So, we will call it B chi. Okay. So, what this will do is that it will sample all these parameters and then it will choose a matrix B from ZQ n minus 1 cross M. Okay. And it will output all this. Okay. So, this is just like setting up the basic parameters in the scheme. So, this is our setup. Now, we will actually choose the public and the private key. Okay. So, key generation. So, by the way, these parameters I will assume are implicitly input to all the algorithms, I will not keep writing it down. Yeah. So, now what key generation does is now it will start looking like the scheme we saw before. So, it will sample some LWE secret S in ZQ to the n minus 1, okay, and it will output T as minus S comma 1. Okay. So, this you will see why we write it like that. This is as the secret key. So, this is our secret key. And for the public key, what it does is it computes an LWE sample as SB plus E, where E is sampled from the noise distribution. Okay. So, the public key will be, we will call it A, which is the fixed matrix B followed by the LWE sample computed with respect to B. Okay. Is it clear? So, I will just highlight our secret key and our public key. Okay. So, note that this is what we were doing even before, just for basic public key encryption also this was our key. It was a matrix and an LWE sample with respect to that matrix. Okay. Good. So, this is we have our public and our secret key. Now, of course, we have to encrypt. So, our encryption will be a little bit different than what we saw what we saw for basic PKE. So, encrypt takes the public key and some message bit, maybe instead of M, it may be good for me to call this something else. Okay. So, I will call it mu because we are also using M for a dimension. So, just to avoid confusion. So, in order to encrypt mu, what do? I sample a binary matrix R. So, 0 1 M cross M, okay, and I compute C as A times R plus mu times G. This is my ciphertext. So, this is a matrix, it is in ZQ n by M. Okay. So, the ciphertext is AR plus mu G, where A is, as we have seen how it is constructed, it is the public key, R is sampled binary random, okay, and G is the matrix we saw before, the powers of 2 matrix. Okay, this is really a very magical scheme. I mean, I have seen it for almost a decade now, and it is still surprising to me that such a simple scheme is fully homomorphic. It solves like a big open problem from like a big open problem in cryptography. I should not say open anymore. So, by the time this scheme was discovered, FHE had been solved, but this scheme gives us a very simple description, which we can hope to present in one lecture. So, this is our encryption. Now, let us define decryption. Okay, so, in order to decrypt, what do we do? Okay, so, remember that my T, my secret key, right. So, my secret key is some T which is minus S comma 1. Okay. What am I going to do? Well, I will define a vector W. So, this is vector is again going to just encode the scaling factor. Remember, like in the basic PKE scheme, we were multiplying the message with a scaling factor and adding it in. This W is also just going to encode a scaling factor, but it will have a bunch of zeros just to make the algebra clean. So, it will have a bunch of zeros here, okay, and then finally it will have q by 2. This is W. Now, compute V as T times C times G inverse of W transpose. This is in ZQ. So, this is my decryption. Now, I have not shown you how evaluation works yet. Okay. But it may be worthwhile to take a quick detour and see why is this even a general public key encryption scheme. So, you know, in particular it is not immediately obvious that correctness should work over here, right. So, let us just take a quick detour and you know just establish correctness as PKE. So, now you will see how the choice of notation makes it quite simple. Okay. So, first thing to note is that the way we defined T and the way we defined A, okay, this is what minus s comma 1 and A is what it is B, right. So, this is minus S B plus B and B is what it is S B plus E. So, T times A is just error E. Okay. So, we can say that T times A is approximately 0. Everyone agrees with that? Okay, very good. So, now let us next see what is T times C for some ciphertext C, right. So, T is you know minus S1, C is what AR plus mu G, yeah, C is AR plus mu G. So, T times AR plus mu T times G. Why do I take mu out? Because it is just a bit. So, I can write T times C as T times AR plus mu times Tg. This I claim is nothing but approximately mu Tg. Why is that? Because T times A is already very small. Okay. So, T times A is approximately 0 and R also was binary, remember. So, R is also a low norm matrix. So, what does this mean? If I multiply a low norm vector by a low norm matrix, then whatever I get as output, its norm can be bounded. Is it clear? See, this is actually the main idea that we use in lattice based encryption, that remember we saw how the message is encoded with a scaling factor, right. So, what we need to do is sort of annihilate the large terms that appear in the decryption equation. The small terms where we are being deliberately vague about what is small right now, obviously that can be made formal, but the things that are you know small, I mean up to some bound. So, let us say that our final bound is q by 4. If you remember you know yesterday we saw this picture, remember. So, we saw this picture that you know if this is 0 q by 2, right, I am scaling my message with q by 2. So, if I recover you know q by 2 m plus error, right, and my error is less than q by 4 for example, then you know when my message is 0 the output will be somewhere here, when my message is 1 the output will be somewhere here. So, they are well separated, that is the point, right. If they are separated, then I can recover the message bit from this. Okay. So, therefore, what I am trying to get at is that you know as long as I have some bound on the error, I can hope to keep going. Now, this is hand wavy and it is also dangerous by the way, because it is not that you know I can just keep doing this. So, I need to be very careful ultimately about you know what is the size of my error, what is the size of my modulus, right. Am I going to encode my bit you know in a way that I can decrypt it? The noise growth should not overwhelm the decryption process, right. We will need to be careful about that and we will be of course, but nevertheless the you know the intuition is rock solid. As long as you know I do not have random stuff over ZQ multiplying my noise, right. If I can bound the noise in some way, I usually have freedom in how to choose my modulus q. I can typically choose my modulus q big enough, so that even if the noise keeps growing, obviously all of this is with caveats, right. So, it is not like we can do this indefinitely and so on, but this is the intuition. So, typically I have freedom on my about how big my modulus can be, and intuitively speaking, as long as I do my manipulations in such a way that the whatever error is there in the ciphertext, it is only growing in some controlled way, like I am multiplying it with a binary matrix. So, fine, I can bound the norm of like what is the norm of the resultant vector when multiplied with a binary matrix and so on. As long as I can kind of control it, the hope is that I will be okay. So, all of this was to say that look, t times a we already said is small, by construction of a and by construction of t. So, t times a is small, we saw this. Now, r is also small, right. So, this whole thing is small. And if this whole thing is small, then let me ignore it. For intuition, at least that is okay. So, I can say that t times c is approximately mu t times g, alright, good. Let us now go back to the decryption process. So, the decryption, what was it doing? It was computing t times c times this g inverse w. So, we have so far analyzed what is t times c, we have only analyzed that. So, now let us look at the remaining terms that will be there in decryption. So, we said is t times c, right, times g inverse w transpose. So, now what is w? W is the zeros with q by 2 in the end. So, let us see what we get. So, now t times c we said is this is t c plus some error, I do not care about its exact value, it is something, g inverse w transpose. Now, first right off the bat, I want us all to observe that somehow it this system has been designed so that what is being multiplied to this error is again small, right, because G inverse is the bit decomposition operation. No matter what input you give it, the output is going to be binary. So, again I have somehow ensured that error times something binary. So, again I can hope that this is small, and again that is going to work. So, I am going to again ignore the noise and I will write this as t times c times G inverse W transpose, right. Now, what is t times c? T times c we said is mu t g, correct, approximately mu t g. So, see how these approximations are working out for us very nicely. Of course, that is the cleverness of the scheme, right. So, because t times c is also not exactly mu t g, right, it is also mu t g up to some noise, but these noises I am just adding them up, right. Later we will have to worry how to control the noise growth, but for now we will just keep going. So, I have mu t g times G inverse W. So, now what did we learn about G and G inverse? They essentially cancel each other. This is also why we are calling this function as G inverse, right. So, this can be written as mu T W transpose, right. And now what is W transpose? Well, and what is T? So, let us write this. So, this is mu, I write this as minus S1, right, and this W is zeros with q by 2. Then the inner product of this is just mu q over 2, okay, and from this I can get mu back. So, this is, it just seems like a slightly more complicated version of the scheme we saw yesterday. Okay. But note that here actually it is also simpler in one way, because we did not use the Hermite normal form of LWE. So, here we are choosing our secret from the standard uniform distribution rather than the error distribution. Anyway, so does everybody agree with me that the correctness holds as a basic PKE? Okay, so now it remains to establish homomorphism. Okay, so of course that is the most challenging part, but as we will see, it has been figured out in a very elegant way. Any questions? All right, so let us stop here. Thank you.